So, why is it that some molecules have a right-handed and a left-handed version like that? If an object is not identical to its mirror image, that object is chiral. And every chiral object has an enantiomer. So, notice the differences between these definitions. Enantiomers are a pair of mirror images that are different. A chiral object is any object that is different from its mirror image. So, an object is either chiral or achiral. Achiral objects are a little easier to spot because they have an internal plane of symmetry, also known as an internal mirror plane. If you can devise any sort of plane that divides that object into two identical halves, then that molecule is not going to be chiral. So if you look at this piece of glassware here, the plane splits it right down the middle. You have two identical halves. Likewise, if I were to look at this in a mirror, its reflection would look just the same as it. However, your hand, there is no internal mirror plane. I could try to do it right down my palm and my middle finger there. That doesn't work because my thumb and my pinky are different. I could try to use the plane all going through all of my fingers, but that doesn't work because my hand only curls forward. It doesn't curl backwards. So when there's no internal mirror plane, then the mirror image is different from it, just like your hands are. So let's take a look at that in terms of some molecules. Take a look at methyl cyclohexane. Okay, six-membered ring with a methyl on one of the carbons. There is an internal symmetry plane that goes through the middle of the ring and through the methyl group. The mirror plane is not in the paper because the methyl group will be coming one direction and the hydrogen will be going the other direction. So that doesn't work. I have to have a symmetry plane going up and down that has two identical halves to it. If I do 2-methyl cyclohexanone, right, same molecule as before, but I put some functionality on one of the sides, like that, the mirror plane that we drew for the last one is no longer valid because we have two different parts on either side of it. So there is no internal mirror plane in that molecule. If I did 2 methyl groups on that same carbon, I could make that achiral, CH3 and CH3, but now there would be a mirror plane in the paper where one methyl group would be coming forward, one would be going back, but they would be reflections of each other. So that molecule would be achiral. So I think one of the easiest ways to identify a chiral molecule versus an achiral molecule is to find that internal mirror plane. If we look back at those tetrahedra that we dealt with, there are internal mirror planes in each of these. When there are two equal groups, the mirror plane will go right in between them. So the red one and the blue one would be in the mirror plane. The two green ones would be on either side of it. So you could try to draw it carefully. If I drew it looking at it from that direction, in between the green ones, like that, it would look like this, and my mirror plane would bisect the molecule that way. So that's why if you have two identical groups, you can split the different atoms in half, but you can have each of the same remaining two atoms on the left and the right of the mirror that way. So that's one way of identifying a chiral object versus an achiral object. If an object is chiral, it has an enantiomer, and the two of them are a pair of enantiomers, a pair of mirror images that are different. Achiral objects still have mirror images, but those mirror images can be tumbled around to make the same thing. So let's look specifically at how tetrahedral carbon factors into this. If we have a carbon that's bonded to 4 different groups, we call that a chirality center. And if there's one of those in the molecule, it will cause the molecule to be chiral. Okay? Any carbon that has a handedness to it, if there's one of those in the molecule, it causes the whole molecule to take on that handedness to it. So you have to look at the 4 groups that are attached If all four are different, even if there's a minor difference, any minor difference can still make them different in terms of their structure. So if I do 5-bromodecane, obviously the H and the Br on that carbon are different from each other, but I have a 4-carbon group and a 5-carbon group. So there are 4 different groups on that carbon. That makes it a chirality center, and we usually mark chirality centers with a star when we're talking about those. So let's mark the chirality centers in a molecule like this. Take a look at this carbon right here. There's a carbon with just 3 lines coming out from it, but carbon makes 4 bonds, so that 4th one must be a hydrogen. There are now 4 different groups attached to that carbon, so it is a chirality center. Nitrogen does not make a chirality center, even though it's sort of tetrahedral-like in its shape. Because of that one lone pair, these 2 groups are allowed to interchange each other, so you cannot isolate just one configuration at either of those centers. In this menthol molecule, there's a methyl group, there's an H going around the ring. One side of the ring's different from the other, so there's a chirality center. Got that OH attached. That's a chirality center. Really, anything attached to a ring like this will be a chirality center because the 2 sides of the rings are different from each other. In dextromethorphan here, the cough suppressant, it's a little trickier to see, but if I look at a carbon, this is a quaternary carbon. There's no H's on it, but still, the groups are different from each other, right? This one has a 2-member, has 2 carbons, then nitrogen. This one has 4 carbons, then another carbon that has a benzene ring attached to it. That one has another carbon. So there's a chirality center. There's one, and there's one. So I count 3 in that molecule.